right, so the car accelerates from 0 to 100 miles per hour within 1 second, right? So what's the acceleration? So let's do that problem. All right. It goes from 0 to 100 miles per hour within 1 second. So the question is the acceleration. And then let's express it in terms of g. Okay, what's the next step? Next step is the conversions, right? Miles per hour is no good, so we gotta express this in terms of meters per second. All right, so multiply this with a conversion factor. So miles per hour to meters per second. And 1 meter per second is 2.24 miles per hour. Okay, so
44.64.
44.64, give yourself. Okay, so give yourself 5 points for that one. All right, so the next step is, given these, which formula would you use?
Second.
All right, given these, I would use the second one. Yeah, very good. So let's pick that one and use the second one. All right, so it's going to be final velocity, initial velocity, and then we have a times t. Cool, so we got that. So what we have, the initial, do we have any zeros? Yeah, initial velocity is 0, so get rid of this. All right, so we got a times t equaling v. Okay, so what's the next step?
Isolate.
Isolate
the A.
Okay, cool. Isolate the A. All right, so get rid of t. And we're kind of done at this point. All right, so acceleration is changing velocity. It's velocity over time in this case. All right, so that's as far as we go. All right, so now the numbers. All right, so
44.64 divided by 1.
Okay, very good. It's 44.64 divided by 1. All right, so that's going to give us, this one is straightforward, 44.64 meters per second squared. Okay, so what do we do? Move the decimal to the left. All right, so that's going to give us the acceleration, roughly. So what is it? 4.5 Gs. All right, so the acceleration is 4.5 Gs. She said 5.5 Gs is 4.5 Gs. Okay, so one of the things that I want you to realize is what these people do is really impressive, but they still feel the need to exaggerate. All right, she got the half right, and she knows it's 4.5. She adds 1 more G to it just in case. All right. The pilot did the same thing. He knows it is 3 seconds. He makes it 1.5 seconds. Okay, just exaggerating. Is it possible that she also lied about how many Gs? She said it's 5.5 Gs, and that's more than what the astronauts experience in takeoff. Okay, so we'll do that later. Okay, before I give you a break, okay, let's take this one step further because this is just an exercise. All right, so A is the acceleration. Okay, so B is the distance that it covers, right? So distance in terms of meters, and let's express it in terms of feet. Okay, so which formula would you want to use for that one? Okay, so once again, you got options.
The third
X,
one?
yeah, you can use the first one or you can use the third one. Okay, so which one is easier? I'm gonna be lazy. I'm probably gonna use this one. It's easier because X is already on the left hand side, right? You can use the third one if that's what you want. I'm just gonna use that one because that's the lazy thing to do. All right, so for part B, I say let's use this. This one is easier to use. All right, so notice that the initial speed is 0. Okay, so which means that this term is going to go to 0. And now you're left with this. It's going to be 1/2 AT squared. All right, now the numbers. So you have 1/2. Your A is this, and T is 1 second. So we got 44.64. 1 squared. So what do you get?
22.32
meters. Give yourself 5 points for that one. And lastly, we have to do a conversion. All right, so convert this to feet. All right, so meters is going to be at the bottom. Feet is going to be on top. All right, so 1 meter is 3.28 feet. And then this is going to give us what?
73.21.
73.21 about 75 feet, right? All right, give yourself 5 points for that. All right, give yourselves 5 points for that. All right, so this was the first couple of them that we did. Obviously, it's how you do it, so this was a good example. All right, so.
Thank you very much, Houston.
We got a couple of housekeeping procedures for you. We'd like you to roll right to 060 to know your rates.
Roger that. Rolling right. 060.
And then if you could give your oxygen tanks a stir.
Roger that. Hey, we've got a problem here.
What did you do?
Nothing. Stir the tanks.
Whoa. Hey.
This is Houston. Say again, please.
Houston, we have a problem. We have a main bus B undervolt. We've got a lot of thruster activity here, Houston. It just went offline. Oh, there's another master alarm, Houston.
I'm checking quad.
There's no reverse now.
Maybe it's a quad.
We've got a computer restart.
I'm going to reconfigure the RCS.
We've got a
when
base
these things
light.
fire, it doesn't make any
We've got
sense.
multiple caution and warning, Houston. We've got to reset and restart.
All right, I'm going to SCS.
Jesus. Fuck, the heart rates are skyrocketing. Econ, what's your data telling you?
O2, tank 2, not reading at all. Tank 1 is at 725 psi and falling. Fuel cells 1 and 3 are, oh boy, what's going on here? Flight, let me get back to you. Flight GNC? Flight, they're all over the place. They keep going close to gimbal lock.
I keep losing radio signals. Flight at
22, do it manually.
One at a time, people. One at a time. One at a time. Econ, is this an instrumentation problem, or are we looking at real power loss here?
It's reading a quadruple failure. That can't happen. It's got to be instrumentation.
Let's get that hat button. The limb line hit by me here.
Yep.
The tunnel's really torquing with all fluid. Houston, we got a pretty large bang there associated with the master alarm. Shit, main bus A.
Main bus A, undervolt.
Houston, we have a main bus A undervolt down 2. It's reading 25.5. Main bus B is reading zip right now. We got a wicked shimmy up here.
Econ, can't see these guys talking about bangs and shimmies up there. Doesn't sound like instrumentation to me.
You are breaking up 13. You get this hatch of steel.
Just going. We've been hit by a meteor. We'd be dead by now. We're going to try to get us out of this lurch.
Houston, you're in the mud. Did you say switch to Omni Bravo?
13.
Roger, and the signal strength on the high.
Fighting me. What's the story here, Jack? We keep floating with gimbal lock.
What's the dispute up now? Okay, Jim. SMRCS, Helium 1.
Switch to
A
Omni,
and C
Charlie.
are barbafold.
Houston, I'm switching over quad C to main A.
Okay, Houston. Fuel cell 1. Fuel cell 3. We got a main bus B undervolt, cryo pressure, superpressor. What do we have? AC bus 1, AC bus 2, command module computer, and O2 flow high. Well, I don't know. Maybe this is a caution and warning.
Houston, we are venting something out into space.
I can see it outside window 1 right now. Definitely a gas of some sort.
It's got to be the oxygen.
Apollo 13. Is it based upon a real event, or is it just made up? What do you guys think?
It was real.
All right, so which one happened first, the movie or the actual event? You don't have to answer that question. All right, guys, the oxygen tank exploded. Oxygen tank exploded all the way out to the moon. They were going all the way out to the moon, and all of a sudden, boom, the oxygen tank exploded. So what do you do under the circumstances? What's the proper course of action? All right, let's run a few ideas regarding what it is we could do under these circumstances. All right, I gotta find Zoom now. I'm losing Zoom. Okay, they had a few options. One of the options that they had and they decided not to use was the most obvious one. Okay, so they're on the way to the moon. Apollo 13 is the example that we're looking at. So here's the Earth. All right, so I'm gonna place the moon right here. All right, so it's like 250,000 miles away. And the Apollo 13, so they take off in the direction of the spin, and then they're moving in this direction. And on the way there somewhere, what happened was the oxygen tank exploded. Okay, and mission is compromised at this point. All right, so they know they're not gonna be able to land on the moon. Tank exploded, but they have enough oxygen. So these guys are going about 25,000 miles per hour right at this moment. All right, so their speed is about 25,000 miles per hour. So why not just stop, put the brakes on, stop, come to a complete stop at 25 miles per hour, turn around and come back home? Do you think that's possible?
No.
Okay, why not? You're thinking that that's not possible because?
Because it would take too much time to stop and then come back to Earth.
Okay, let me ask you this question. How do they stop then? What is it that they need in order to stop in space?
They need equal thrust in the opposite direction.
Okay, they need thrust in the opposite direction, right? Where did they get the thrust from in the opposite direction?
The boosters.
Okay, so I'm going to give you 5 points for other discussion. Guys, what they need is rocket fuel. I mean, the rocket fuel is what got them up to that speed. Now, what they need to do is they need to fire their thrusters in this direction in order to generate a force in the opposite direction, right? So my question is, do they have enough fuel in order to stop in space? What are you guys thinking?
I mean, if they had enough fuel to make it to the moon and come back, then they should have enough fuel to come back.
Okay, that's not the answer I was looking for. I'm going to give you 5 points for that one. The rocket fuel that they have, guys, the rocket fuel that they have is, you guys are thinking that traveling in space is like driving a Ford Tempo. It's not, guys. You reach 25,000 miles per hour, you shut off the engines. They will just coast all the way to the moon at 25,000 miles per hour. There's no friction to slow you down, and there's no reason for you to go any faster. All right, so you will maintain your initial motion. Okay, so these guys are already coasting at 25,000 miles per hour. Got it? All right, so what do they need in order to stop? They need enough rocket fuel to stop. So they have enough rocket fuel to actually go from 25,000 miles per hour to 0. And you would think no, that's a lot of rocket fuel, guys. Would they be carrying that amount of rocket fuel in order to actually stop in space? I would say no. I thought the answer would be no. And eventually, I started reading a book on the history of Apollo 13, the details. I was rather surprised that these people had enough rocket fuel actually stop in space. Not only do you have to stop in space, also now you have to turn around and you have to accelerate in the opposite direction and get up to the same speed. They had that option. So they decided not to exercise that option because there are problems with that option. It makes it much more complicated. So they decided that they're just going to slingshot around the moon. All right, so we will go around and then slingshot and then come back home. They figured that they had enough oxygen to carry that. Now, if you want to carry out something like that, so this would become the trajectory of their motion. All right, so you will just slingshot around the moon and then come back home. Boom, 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 boom. Okay. The problem with that is, number one, it's not a problem. The next solution is, now you have to slow down. Okay, so in order to slow down, you have to rocket the fires for a while in this direction. So you have to generate a negative acceleration. All right, and while you're getting into the moon's gravity, and you have to be moving at exactly the right speed. And then, so you have to fire the rockets for a while and then bring your speed down and then use the moon's gravity to slingshot. And then in order to escape from that gravity, now you have to speed up. So now you have to have a positive acceleration. Acceleration is getting positive on this trajectory. And then, so now you have to have a positive acceleration. And then at some point on the way back, in order to say you're going to be here, okay, now you have to slow down so that you change the trajectory. You have to angle it just right so that you're not burning out. Again, you have to fire the thrusters and then slow down significantly before hitting the atmosphere because you don't want to burn up. Okay, notice that things are happening here. Number one, you can design a free return trajectory. You say, okay, these guys are here, we'll do a slingshot, and then you, which means that you can figure out the landing zone first, and then set up your trajectory and get this rocket in that trajectory by using uniform acceleration. Uniform acceleration. In that sense, you make motion 100% predictable. And this is the course of action that they decided to follow. That's what they did.